Hello and welcome to the third video in the series on Newton's laws. In this video we'll look into free body diagrams, how they relate to the net force and how we can use that to calculate different things, and also we'll get an introduction to friction and how that relates to the motion of the object and to free body diagrams. We'll cover the terms on the left during the video, and also on the right you'll notice a diagram. This is a representation of a free body diagram, and something that we've seen before. We can see that the two forces vertically are balanced, the idea being that this would be a solid object standing on a surface, could be like a book sitting on top of a table, being pushed, in this case, to the right. The vertical forces are equal and opposite. We could say that they are in equilibrium. So a review of that term is to say when forces are equal and opposite, equal in magnitude, as in how much value they have, and opposite in direction, they will oppose each other and sum to zero. In other words, they add up to zero. In the horizontal direction, we only have one force. And since we only have one force, that means that this force is our net force. And that means that our net force, which as you recall equals ma, can be solved. Alrighty, let us move on. A quick review and overview of what's going to be covered. Free body diagrams are supposed to be a simple image of forces acting upon an object, and they're drawn as vectors on the object. And vectors are something that have a magnitude and a direction. I'm kind of skipping down to here right now. A vector has a magnitude and a direction. Just to really review that term, as I know some people have heard that and they go, wait a minute, what's a magnitude? Magnitude just means how much. So if I said, here's a force arrow, and it is 150 newtons to the right, then the magnitude would be 150 newtons, and the direction in this case would just be to the right. So just to review that idea, it will become important as we go through this. What we're going to be able to do by drawing these free body diagrams is we're going to be able to find net force, mass, or acceleration, any number of those different things. That's kind of the idea. So as we go through this, keep these ideas in mind, and please do not forget net force. If there is a net force, it will produce an acceleration, and that acceleration is calculated using this equation. And by the way, this would be Newton's second law. So let's give this a try. First example is, say we have a book on a frictionless tabletop. If the book is being pushed to the right with a force of 18 newtons, find the following. And we will draw a free body diagram, and we will also find the acceleration of this book. All right, first off, as I said, we want to read, we want to underline important details, and then kind of draw things out. So first off, frictionless tabletop is important. That means no friction means it looks like we won't have anything resisting this motion to the right. And there's a force that goes to the right at 18 newtons. It's being pushed, so we could call that a force applied. So I have some force applied that is 18.0 newtons to the right I could draw. That was my magnitude and direction. And with this is actually asked of us. We're actually asked to draw anyway. So in our order of doing things, we have to draw this anyway. Now it's on a tabletop, so first off, we assume this thing is on Earth, so there must be some kind of gravity pulling it down. I'll label it Fg. And if it's on a solid tabletop, any solid object, there should be a normal force. And for the sake of this video, I'm just going to label it Fn and not do my horrible scripted ends that are hard to read. I have a force pushing to the right. I choose to draw my arrows from the center of the diagram. I find that to be easier to do and things get less cluttered and it's less confusing. I'm going to call that some force applied, even though I know the value of it. I just want to label what I know so far, and we'll put values to it in a moment. Something we can say right off the bat is that since this is on a tabletop and it's not rising or falling off the tabletop, it's just moving to the right, there's no motion vertically, normal force and force of gravity must be in equilibrium. They must be equal and opposite. So I kind of can say something from this. If they're in equilibrium, they're equal and opposite, I can say that force of gravity is equal to the normal force. This will become important later on. Well, our diagram is complete, but now we're supposed to figure out the acceleration of the 2-kilogram book. We already know there is not going to be a net force vertically. In other words, there is no overall acceleration vertically. We're looking in the horizontal direction, though, and there clearly is a force. And there's nothing opposing this force. This would be known as an unbalanced force. Newton's second law says that whenever there is an unbalanced force, whenever you have a net force, an overall force that is higher, you will have an acceleration in that direction. And this F net must be equal to ma. Well, we already know what the net force is. It's just Fa. That's the only force that's working unopposed. It's got a total value of 18 newtons overall. And that must be equal to, they gave us the mass here, 2 kilograms times the acceleration. Now from here, perhaps it'll be easier for you to see the work if I move this. We divide by 2 kilograms on both sides. It looks like my acceleration will end up being 9 in its meters per second squared. Now there's another part of this though. An acceleration has a magnitude and a direction. And if the net force is going to the right, the acceleration must also be going to the right. So I could draw an arrow to imply to the right, or I could state to the right. You wouldn't want to say east in this case because we don't know if that book is actually being pushed to the east on the tabletop, but we do know it says to the right. So we'll say to the right. Quick review of things we saw. We found out that that there was a force of gravity opposed to by a normal force. Those two are in equilibrium. Newton's third law said every action has an equal and opposite reaction. Then the force of gravity pushing on the tabletop results in a normal force pushing upwards, and they're equal and oppositely opposed. You may recall, though, that the actual action-reaction to the force of gravity is the pull of the book on the Earth compared to the pull of the Earth on the book. But in this case, we can still state the third law to say that we have a normal force opposed by a force of gravity. They are equal and opposite, which means there's no net force. We went on to use Newton's second law to say that if there's a net force, it must equal mass times acceleration. We are therefore able to calculate that acceleration and figure out the acceleration of the book and verify, well, barely verify the answer. And when I say verify, I wanted to actually clear up the idea that the net force goes to the right. That whichever direction the net force goes to in this case is the same direction as the acceleration, so our net force was to the right, which means our acceleration was also to the right. Alrighty, here's the basics on friction. Friction is a force that opposes motion of objects, any motion of the object. It basically is opposing any forces that are acting on it, or any motion at all. If it's already in motion, it'll actually try to slow it down. It's trying to get it to be at rest. And it can be caused by a number of things. There are actually a couple versions of friction. We have a type of contact friction between surfaces. That's where, like, you think about that book before, a book's on a solid tabletop. Well, there's going to be friction between the two surfaces. And the reason for this is actually the fact that there's attraction between the molecules of the book and the table. They want to bond to each other and stay stuck to one another, and that kind of slows the object down. These bonds that form resist the motion of it. It tries to lock it together so it can't go anywhere. Kind of like glue. The rougher the surface, the more areas there are to make contact, and the more likely they are to get stuck to one another and therefore have more resistance to motion, kind of like sandpaper versus the smooth tabletops that you have on your tables. Your tabletops are very smooth, so your book slides across them rather easily, or say like your notebook can slide across it rather easily. Whereas if I was to put paper, like sandpaper, on top of that, not going to slide so well, because it's rougher, and rougher objects have more contact areas, allowing for more friction. There's another version of friction, which is contact with a medium. And when I say medium, I mean like liquids or gases. So, for example, a gas, you think about air, and for a liquid, the best example is probably water. So if you've ever been swimming in a pool, you've experienced friction. You've experienced the resistance of that medium, the water, not wanting you to continue moving. It resists your motion. And this is caused by the interaction with the molecules of the medium colliding with, or attempting to bond with, perhaps at the same time, the object that is in the medium. There are a couple of ways to calculate these things. I'll give you the equation, and we won't use it today, but friction is calculated by a coefficient times the normal force. We will go into this more in detail later. Whereas resistance, which is abbreviated R, is equal to negative BV. And that's an interesting thing. I believe in the last video we talked about how it's caused by the velocity and some properties of the medium and the object. We'll get into this one a little more later. Now, to draw a friction arrow, friction has to work in opposition to the motion of the object. In other words, if you have an object moving to the right, friction's pointing to the left. A surface friction arrow is always drawn on the diagram where the surface is making contact with the object, and it's labeled with script F. So if this was my book, and we did the same example as before, it's being pushed to the right, it's a force of gravity. Tell you what, hold on, I'm going to start this somewhere else. Sorry about that, I just wanted to get a little more room so you can see. Now the friction arrow would be drawn in opposition to the motion. The book is trying to go this way. And by the way, whenever you draw a vector that's not a force vector for a free body diagram, it's got to be totally separate. So like this velocity arrow that I drew up here, I drew it completely separate of the diagram because that's not a force. For a free body diagram, forces can't be on the object. So I would label this with a script F to stand for friction. And if I could calculate the value of it, I could figure out what our actual force is now. Because now it's going to change what our net force is. We're going to have a certain amount of force applied going forward. So I basically have FA going to the right, and I'm going to add that to friction going to the left. And that's going to equal my net force. So the right would be positive in this case. So I basically have a positive FA plus friction going to the left would be like a negative friction. And that must equal the net force working on the object. And then that overall amount of newtons, however many newtons are left over, is going to be equal to MA. We'll go into an example to kind of look further into this idea. We'll use the same example as before, except add friction to it to kind of build upon what we already understand. So we have the exact same idea where there's a book on a tabletop and it's being pushed to the right with a force of 18 newtons. Okay, find the following. We want to draw the free body diagram of this first. Now, it doesn't mention that there's not friction. We should probably assume there is. And by reading on to question B, we notice that there is definitely a force of friction, and it has a value. So there's our mass, and we know that this force of 18 is to the right. So let us draw this diagram first off, and we'll be able to figure out what to do from there. Start out with an object. It's always very simple. A book can be represented as a simple square or brick. And we have a normal force opposed to that. They are in equilibrium, which means they're equal and opposite. No net force in that direction because it's not moving up off the table or falling through the table. And then we say we have some force applied going to the right. And now the key one that's different is we also have to have a force of friction. The contact between the book and the surface would happen on the bottom of it, which is why I draw the arrow like that. You may be thinking in your mind, well, why do we draw the arrow different than the other ones? It's just another force arrow. Why should you draw this one on the bottom of it and the other one on the top of it? Or from the middle of it? The reason being is that when friction occurs, we want to show where it is happening from. Normal force and force of gravity actually work on the center of mass of the object, which is why we draw them from the middle. The force applied works on the object from wherever it makes contact with it, but it's still just pushing the center mass of the object. Force of friction is only making contact with the object on the surface in question. So that's why we draw it like that. It also leaves room for other arrows in case you had maybe another force applied up here that was pushing to the left. Something like that. Obviously in this case we do not. So first off, a couple of things we can say is we know that this has a value of 18 newtons. I know that this has a value of 7.5 newtons. I could probably find the force of gravity if we wanted, but I haven't been asked to do so. If I was, though, I could say that since the normal force and force of gravity have to be equal and opposite in this case, I just find the force of gravity and I know the normal force if asked for that as well. Anyway, let's move on to the big idea here, which is to find the net force. So the net force this net force is the sum of forces acting in a direction. When I should say dimension. Let's say dimension instead of direction. That'd probably be a little more clear. Keeping in mind that we can separate x's and y's, that's the reason why I clarify this whole sum of forces acting in a dimension. You can have a net force going vertically and a net force going horizontally, but keep in mind you have to separate the horizontal and the vertical motion. We can do that just because of how things happen to work in this universe. Now that's also equal to ma, and that might be that'll be a step we'll get to here. That net force always has to be equal to ma, because a net force results in some acceleration. It should be calculated through that method. So let us take that idea. Sorry about that. Fun with a smartboard. And let us add these two together. We essentially have in the horizontal direction a couple forces being combined. I have a positive Fa plus a negative friction, and that must equal my net force. So I can plug in the values for that, seeing as we know them. 18 newtons minus, I don't need to have the plus and negative sign again, 7.5. This must be equal to my net force. So 10.5 newtons must be my net force. That would be to the right, by the way. We just have a magnitude. We need a magnitude and a direction. Now, in order to find the acceleration, which is what we're looking for, we also have to recall Newton's second law, which is that F net equals ma, we're going to plug that into the equation here. So I basically have my 10.5 newtons is equal to net force, but net force is equal to ma, so I can plug in ma there. So now we say we have our 10.5 newtons net force, which is equal to the mass, which we recall is 2 kilograms, times a. And if you divide both sides by 2 kilograms, we can now figure out the exact acceleration of this object. And it turns out to be 5.25 meters per second squared. One more thing, to the right or with an arrow, right. So again, net force produces an acceleration in the same direction, or sorry, a net force produces an acceleration in the same direction as a net force. I'm not sure if I said that clearly at the first part, but a net force results in an acceleration that is in the same direction as the net force. So whichever way net force goes, so does acceleration, every single time. That doesn't mean that the object has to be moving that way. So that's another thing to clear up, is that just because you have a net force going to the right in this case, doesn't mean it was originally moving that way. Obviously in this problem it was being pushed to the right, so we assume that is the way it's going to go. That's the direction for the velocity, that's the direction for the acceleration, which means this object must be getting faster. But if we were to, say, talk about a car applying its brakes, its motion would be whichever way it's going. So in this case we'd have a car, and let's say we have it driving to the left. So velocity is going left, and it's a car, so it's got a force of gravity acting on it. It's got a normal force acting on it. Let's ignore air resistance. And we assume it's just kind of coasting to a stop. And let's say it's because of friction. Then I could draw a friction arrow here, and I could say, well, there's my car slowing down. And I've clearly got the force pointing opposite of the direction of the velocity. So acting in opposition, slowing it down. And by the way, in this case, these are equal and opposite. Your net force is friction, and that net force of friction must be producing some acceleration. And since that acceleration is opposite to the motion of the object, it is slowing down. Final example, a little tougher. And you'll want to start drawing this one out. So we have a 4 kilogram block pushed to the right with a force of 82 newtons. And if this block is accelerating at a rate of 3.0 meters per second squared, find the following. We will find normal force acting on this, so looking for normal force, and the force of friction acting on a block if it's accelerating at this rate. So I know mass, and I know the acceleration, and we're going to figure out more from there. First off, we should probably start with a free body diagram, even though it's not asked of us. It'll be easier to understand what's going on if we do draw it out. We know there's a force of gravity acting on this block. There must be a normal force as well, opposing its motion. The applied force was to the right, and there is friction acting on it, so we better draw that in opposition to the motion. And the applied force is trying to move it, so we assume that the force of friction would be opposite of that. Normal force and force of gravity are equal and opposite, and that leads us to the first question. How are we going to figure out the normal force acting on this block? Well, if these two are equal and opposite, it would imply that normal force must equal force of gravity, except it's opposite in direction. Well, we're just looking for the normal force. We can tell it's going upwards. Let's just find the value. Easiest way to find the value is to work with something we know, and that would be gravity. Because we know force of gravity can be calculated with m times g. So in this case, m times g, we would just take our mass of 4, multiply it by 9.8, and we should get 39.2 newtons. That would be our force of gravity. And since the normal force is equal and opposite to that, we can simply say that this is 39.2 newtons upwards. So that's an easy one. Question A is actually kind of simple, because all we had to do is figure out, well, the normal force is equal to force of gravity. So we just calculate the force of gravity, and we know the normal force. Next part's a little more complicated. And this is a tough problem, so be aware of that. So we know that these two, we know that these two are going to add together and equal some net force. So we're really going to be having force applied plus a negative friction, and this must equal F net. And as we saw before, F net has to be equal to MA. Sorry, I'm having issues with the smartboard. Interestingly enough, as the video goes longer, the difficulties of the smartboard increase. Alrighty, so anyway, we know the force applied is 82 newtons. I have no clue what friction is. We're solving for that. But I know that this is equal to m times a, because F net is equal to ma. And I do know the mass and the acceleration. So we say that, well, this is 82 newtons minus friction is equal to our mass of 4 kilograms times the acceleration of 3 meters per second. And really, this is it. We just have to solve this. We end up with 12 newtons over here. Kilograms times meters per second makes newtons. 82 newtons here minus friction. And then what I'm going to do is I just need to move stuff around. So I'm going to move friction to the other side. So I now have friction over here. Gets me 82.0 newtons is equal to friction plus 12 newtons. And then from there, I'm just going to subtract both sides by 12. And I should be set to go at this point. And it looks like friction therefore equals 70 newtons. And there we are. That must be the value of friction based upon the situation we were given. If you have any questions on this, please let me know when I return, or send me a message on Edmodo, or just ask around. Good luck on the sheet. The sheets I would have you focus on are assignment 3.4, which looks like this. You should have already gotten this before, otherwise there are extra copies you could ask for. And if you are done with that one, move on to the sheet 3.5 that you got today, which relates to normal force and friction problems, and will introduce you to the actual method of calculating friction. Thank you for your time.